In this video, we're going to learn how we approach definite integral problems when the information that we're given is in graphical or numerical form. Here's an example. This graph shows the velocity of Karen riding her bicycle along a straight road from home to school. The velocity is measured in miles per minute, and our time element is measured in minutes. Using correct units, we're supposed to explain the meaning of this definite integral. Well, I recognize that this type of definite integral represents the total distance traveled in miles from t equals 0 to t equals 12 minutes. Remember that a good interpretation includes a noun, the units, and the appropriate time element. My next task is to find the value of this definite integral. Normally, if I'm looking for the value of a definite integral, I would use an antiderivative and the fundamental theorem of calculus. In this case, that's not possible because I don't have an equation here. I'll have to make use of my graph, and remember that a definite integral can be interpreted as the area between the function and the x-axis on the interval from a to b. In this case, I need to be particularly careful because this absolute value is going to take this portion here, which I might think of as sort of like a negative area, and reflect it across. Calculating the area of each one of these little regions, for example, starting with this triangle, is 1/2 the base of 2 times the height of 0.2. Gives me a value of 0.2. Plus, this next region would have the same amount of area. Plus, I have another triangle, which is 0.15. Then I have 0.3. Here I've got 0.25 square units of area. This rectangle here is 0.6. And then finally, this rectangle right here is 0.1. Remember, it's fine for us to leave our answers in this form. We don't actually have to do the arithmetic to come up with a final answer. In our next example, instead of having a graph given to us, we've been given a table of values. We again have velocity information given, this time for a rocket. The first thing we need to do, using correct units, explain the meaning of this integral. Well, I notice that we have positive velocity. So I could have absolute values here, and it wouldn't make any difference since the velocity is already positive. That way I can interpret this as the total distance traveled by the rocket in feet from t equals 10 seconds to t equals 70 seconds. There's my correct interpretation. Next, I'm asked to use a midpoint Riemann sum with 3 subintervals of equal length to approximate the value of this definite integral. So I'll write on my paper the integral from 10 to 70 v of t dt is approximately, and then I start thinking about a Riemann sum. I remember a Riemann sum is basically doing the sum of rectangles. And so if I'm going from 10 over to 70, well, 70 minus 10 divided by my 3 equal subintervals is 60 divided by 3, or 20. Each rectangle will have a width of 20. So there's my first rectangle, there's my second rectangle, and there's my third rectangle. I now know the width of each of my rectangles. But what height will I use? Well, it's a midpoint Riemann sum. And so that means I need to use the height that's right in the middle of each interval. This will be for my second time interval and for my third time interval. So, calculating the area of these 3 rectangles, the first one, I have a height of 22 feet per second. And then I'm going to be using that for a time period of 20 seconds. Plus, the second rectangle, I'll be using a height of 35 times the width, again, of 20 seconds. And then finally, this is a height, 44 feet per second times 20 seconds. Again, it's not necessary for me to do the arithmetic to come up with a final answer. I've shown that I have knowledge of how to calculate a midpoint Riemann sum. In another part of this problem, rocket B shows up. Rocket B is launched upward with an acceleration given by this equation, measured in feet per second per second. At time t equals 0 seconds, the initial height of the rocket is 0 feet. Initial velocity is 2 feet per second. So initial velocity, that means time 0, is 2 feet per second. Which of the two rockets is traveling faster at time t equals 80 seconds? And explain your answer. Well, it's easy to figure out the velocity of rocket A. The velocity of rocket A at the time value of 80 seconds is 49 feet per second. To determine which rocket is traveling faster, I need to compare the velocities. How will I get from acceleration to velocity? Well, I'll have to use an integral. A lot of students would probably just integrate from 0 to 80 the acceleration, but that would be a mistake. I need to make sure that I include this initial velocity of 2 feet per second. So the initial velocity of 2 feet per second plus when I integrate the acceleration, I'm going to get the change in the velocity. So 2 plus the integral from 0 to 80, and I'm going to go ahead and rewrite this as t plus 1 to the negative 1/2 dt. Notice that this time, in evaluating the definite integral, I'll have to use an antiderivative. I sure hope my calculus skills are good. I've got 2 plus, here if I do the antiderivative, I'll have a half power. And then dividing the coefficient of 3 by my new exponent of a half, I'm going to get 6. I'll have to evaluate this from 0 to 80. Luckily, these numbers turn out pretty nicely. I have 2 plus, here when I plug in an 80, well, that's 81, and I know that the square root of 81 is 9, times 6 is 54, minus, when I plug in the 0, I get the square root of 1, which happens to be 1. So I have 56 minus 6 gives me a final answer of 50. Therefore, rocket B is traveling faster. Notice that we've evaluated 3 definite integrals in this video. The first one we did geometrically, the second one we used Riemann sums, and in the third one I used the fundamental theorem of calculus. Thanks for listening. Enjoy calculus.